This lecture is about standby electrical power. We will cover the topics of the need for standby electrical power, diesel generators, the components of diesel generators, the types of loads that are supplied by standby power and the means by which diesel generators are rated. And finally, we will deal with automatic transfer systems. So let's begin with a description of the need for standby generators. Electrical power is generally supplied in the form of AC, and this is usually in most countries through a national power grid, excuse me, through a national power grid which provides power throughout the country or throughout the region in the form of AC. So that is alternating current transmitted and distributed to where the consumers are from the generating points. But we have sometimes unreliable national grids or sections of grids that may not be reliable enough for the customer's needs, in which case we would require standby generator sets that would provide a secondary source of electricity for the consumers. These secondary forms of power supply can take several forms. So you have prime power supply, which is usually mains electricity. Standby power can take the form of diesel generators, and increasingly nowadays it can also take the form of solar power systems, also known as photovoltaic. Now, the advantage of solar power systems is that their input is free. They are run directly from the power of the sun. So light shining on solar panels is converted directly into electricity. The only disadvantage that they have, and the reason why they are not as widespread in terms of standby power usage as diesel generators, is that they require power batteries, or rather they require battery packs in order to be commercially viable. As you know, electricity must be generated as soon as it is required. So in order for you to take power off from a system, you need to be able to have a source of that power available at all times. So in the case of solar power, the source of power for the system from the point of view of the system would be the battery pack. If, for example, your standby power is required at night, you would not be able to get power from a solar system since the sun is not shining. So you would require batteries. Now, the disadvantage, of course, is that while solar panels in recent years have become quite cheap, battery packs and systems for inverting the power that is generated by solar panels are still quite expensive, and the technology has not yet come down in cost, which leaves us with diesel generators as the most common form of backup power supply. These consist of generator sets with diesel engines that are mounted close to where the consumer requires them. And generally, they will look something like this. This is the format in which they will operate. So you will have, simply put, an engine, a diesel engine, coupled to an alternator. So this is the alternator. It's as simple as that. So an AC generator is mounted directly onto a diesel engine, which rotates it, and then you have power being taken off from the three-phase supply that is generated at this end, right? All the requirements of the generator are included, which will be listing them below. So the parts of a standby generator, you can zoom in slightly, are shown here. So this is kind of a 3/4 front view and a 3/4 rear view. So when we look at the front view, you can clearly see where the engine is, and you can see where you have your alternator, right? So those two are the main components of your power supply, your standby generator. Yeah. When we talk of the engine, there are those associated components that must be forming part of it. Of course, you need to have a way in which you can take in air for purposes of combustion. So that is taken through your air cleaner, which is number 2 there. And it is taken into the engine, as we have said. Attached to the engine, you must have a vent through which you will be able to take on the air, and at the same time you must have exhaust. So actually number 8 is your exhaust. All right. Additional to that, this component at the back, which is much more clearly seen from here, this is your radiator. Diesel engines run very hot, so generally you would have a system that would be able to cool your engine. You will notice that the radiator of this engine is much bigger than what you would find, for example, in a vehicle. The reason, of course, is this is a stationary equipment, so it cannot take advantage of the movement or the wind caused by the movement of a vehicle. Some more components of that are this. Generally, you will have a fuel tank that is mounted below the generator itself, and that is filled through your fuel inlet. So the refilling of the tank is carried out through a fuel inlet that is mounted onto the tank itself, right? Various other components, so like you have a level meter that shows the level of fuel that is available within the system. So your generator, once running, would require some kind of control, and that is the control cabinet that you can see here. As we have mentioned, the amount of power that is generated must match the load that is taking that power or consuming that power. So in order for us to do that, the generator or the engine itself must be controlled in terms of the amount of power that it provides, or the amount of actual kilowatts that it is providing to the alternator, right? So that is done through the control cabinet, which has a governor that controls the operation of the generator. The work of the governor is to regulate the amount of fuel that is provided to the diesel generator, and by extension, it also varies the amount of power that is generated from the alternator. Yeah. Remember that you must provide your power at a specified voltage and frequency. The voltage is controlled by the alternator, right? That one is fixed within here, and the alternator itself has its own regulatory apparatus. The frequency is controlled by the speed that the engine is running. So when we talk of the governor has to maintain both the amount of power that is being supplied, and also it has to maintain the speed at which the generator can run. It must run at a constant speed. So there is constant adjustment of the parameters of the generator, both in fuel and so forth, to ensure that you are supplying the amount of power that is required, as it is required, and when it is required, right? So additional components of the generator set, of course, you have to have a battery. The purpose of the battery is, of course, to crank the engine or to get it started from a cold start. The assumption being that a standby generator will not have power from elsewhere. Yeah, if you're using a standby generator, it means your main supply has been disconnected, so you do not have access to it. So therefore, it must have a battery that will serve to start it or start its operations. Then various other accessories. You can have a lifting lug, which is here. That is for movement or for portability. Vibration isolator that prevents damage to the floor and the surroundings of the engine as it vibrates, and ensures a secure mounting point for the engine itself. Then, of course, mounting flange for the vent pipe. That is for chimney, the exhaust, which we already mentioned. So those are the main components of a diesel generator in the form of a standby genset. So some of the considerations that we would need to look at in terms of generator sets would be including the rating capability. So let's look at generator rating capability. So when we are looking at the types of generators, there are various applications into which generators can be used, or standby gensets can be used. There are those applications where the generator provides prime power or continuous power, in which case the first type of rating that you have is that the generator provides continuous operating power. In this kind of rating, this is defined as the amount of power, the quantity of power that a genset can operate a continuous load. So operate a continuous load. A continuous load at an unlimited time, right? So it is how long will the generator be able to run a specific continuous load, a fixed continuous load at an unlimited amount of time? What is the maximum load that you can run the generator indefinitely, right? And this is measured in kVA. That is a load of how many kVA can the generator run continuously, okay? Remember that this is limited by the amount of heating that the generator will undergo. In our diagram, we saw that a large proportion of the components of the generator are dedicated towards cooling. You saw the size of the radiator and all the pipes that are moving, circulating coolant in the system. This means that whenever we are sizing or we are giving the ratings of our generator, we must list down, or rather we must take into consideration the heating aspects, and that is the primary limiter of the amount of power that can be supplied by the generator. If the generator overheats, there is risk of insulation breaking down, or even the conductors and windings within the generator overheating and melting. So that is the first type of rating. The second rating is prime running power. This is slightly different from the continuously operating power. So this is the maximum power that the genset is able to supply or operate a variable load for an unlimited time. All right. So in the first continuous operating power, you are assuming a steady level of the load, a steady number of kVA. In prime running power, your load can vary. It can be less or more depending on the application that is there. Generally, the kVA rating for a prime running machine would be lower than continuous operating power. And it is important to note that the same machine can have different ratings for each of these. So a generator might be rated, say, 500 kVA continuous operating power, but if its application is prime running power, you can then change it to even more than that, say 700 or 800 prime running power, because of the variation of the load, it will not heat up as much as in terms of continuous power. And the third type of rating is the limited power or standby power. So this is the most common type of rating, and this is where you can note that you have your generator running intermittently. So it is defined, it is a specific definition. So the maximum power that the generator supplies up to 500 hours per year, and 300 of which can be continuous. So generally, this would be the highest kVA rating of your generator. Same generator can have 3 different kVA ratings, the highest of which would be your limited power, because if it runs for a given period of time and then it stops, it has the capability of cooling down and being ready to run once again. So if it is intermittent running, you can get away with operating loads that are much higher than what would be there. So another aspect of the rating capability of a machine is that generator loading, as I've mentioned, is limited by thermal capacity. In other words, the machine, the amount of power that can be supplied by a genset is limited by how quickly it can dissipate the heat that is generated by the engine. Yeah, if an engine is running continuously, it generates heat within its components. The capacity of the genset to dispose or dissipate this heat is what determines the amount of power that it can generate. So this is measured in terms of the maximum allowable temperature rise. And this is defined as the total temperature limit, which is given by ambient temperature plus hot spot margin plus temperature rise limit. So the total temperature limit is the total temperature that the machine can reach safely. The ambient temperature is defined by the temperature of air that is entering the machine. So usually that is given by about 40 degrees Celsius. So the air that is surrounding the machine as it is running, the genset as it is running, usually temperatures will be approaching that amount. Hotspot margin, as the machine is running, the outer components will heat up or will be at temperatures that are less than the innermost components. So you would expect that components in the center of the machine, the rotor of the machine and the windings of that rotor would be higher in temperature than the external surfaces of the machine, which are exposed to the air and are able to dissipate the heat that they contain. So we will add a margin to that of about 10 degrees, which takes care of the difference in the temperature from the outside to the inside. It takes allowance, makes an allowance for that. Then the temperature rise limit would be now, of course, the difference between the maximum temperature limit which the machine can withstand and the ambient and hotspot margins. So generally, you can have different temperature rise limits depending on the ratings of the machines that you're having or the ratings that you are making use of. So for example, so the temperature rise limit generally is 80 degrees for continuous operation. For prime operation, it can be higher than that, 150 to 125 for prime. And you can have 130 to 150 degrees for standby operation. Standby. Meaning that you are able to intermittently operate the machine and it can reach much higher temperatures if it is given an allowance to cool itself down. Right. Next, let's look at the conditions when you are setting a generator rating. So some of the conditions that affect or that determine generator rating. So when you're setting up a generator or you're sizing a generator and making a decision about what generator to use for a specific application, there are a number of conditions of the environment that the design engineer would need to take into consideration when sizing the generator for their application. The first of these is altitude. So in terms of altitude, what altitude affects the generator sizing is that at sea level, air density is much higher than at higher altitudes. So air density. At higher altitudes, you would need to take that into consideration because air is usually the main means by which gensets cool themselves. So if the air density is lower at higher altitudes, you would find that you would need more air must pass over the machine in order to dissipate the heat that is being generated at a higher altitude. At a lower altitude, the air is thicker, so it is there are more air molecules coming into contact with the surface of the machine. But at higher altitudes, there are fewer. The density is lower, so you need more air to pass over, the more volume of air to pass over the machine in order to cool it. So generally, this is taken into consideration by adding for every 100 meter rise, the rating is reduced by 1%, right? So every 100 meters that you go up, you must reduce the rating by 1%. So you can imagine high altitude areas like Nairobi, you would take into consideration the amount of energy that the generator can dissipate. The second factor that we must consider is heat. The temperature in which the machine is operating will affect the maximum temperature rise. So if you have a higher ambient temperature, the margin of temperature rise limit is reduced. So if you are operating in higher climates, you need to derate the machine. If you're operating in colder climates, you can get away with more load being supplied. So higher temperature climates, you must derate the machine. Derating simply means you reduce the amount of power that you are designing the machine for. The third condition that we must take into effect is corrosive environments. If you have corrosive environments, you must have special coatings and protections. So special protection of the genset to provide to prevent special protection to prevent corrosion. This would generally mean that if you have a thicker or more durable layer of insulation or paint or protection on the machine, this means that it can dissipate heat at a lower rate. So you have to derate the machines due to any special protection. So you derate. Number 4 is humidity. So this affects machines in that if it is a very humid area, you may have to have extra protections against the effects of water, which would tend to affect how you cool the machine, or how you additional provisions that you must put in place to take care of the humidity that is around. So places like Mombasa, the Kenyan coast, which have humid areas, you need to consider that when you're rating your generator. So generally you would have a higher, or rather you would derate due to the effects of that. And another consideration, number 5, would be dust. So in areas where there is a lot of contamination in the air, dust and other particles within the air, you would then require filters in the air intakes of the machine, in which case you would then be restricting the airflow. That of course means that you have to derate, because the machine that you're using, if it was taking in air without any restrictions, it would be able to take in more air, and hence combustion would be operating much higher. But because the amount of air that is being taken in is lower, then you have to derate the machine, because it will not be able to attain the high powers that you might be planning to supply. Next, let's look at automatic transfer systems. So automatic transfer systems are systems by which the power can be changed between two different supplies. So in the case of standby power, this is a system that identifies conditions that show that the main power supply, or the prime power supply, is no longer available, or it cannot be provided in the manner that is required, and it switches over from the main power supply to a standby power supply, such as a generator. In addition to that, automatic transfer systems usually also have the ability to start up generators in such conditions, so that you don't have your standby generator running throughout. It just runs when it is required. So the characteristics of these types of of these kinds of systems are the following. So it must be able to operate normally in all power conditions, in all power conditions. So whether it is on prime or on standby, the system must be able to operate. Number two, it must determine the system condition. Must determine system conditions that warrant transfer. So as we said, the automatic transfer system must be able to identify when the system requires a changeover, when it needs to change to an alternative power source, and likewise, when the main power supply is back to normal operating condition, it must be able to identify that and switch back to the main or prime power supply and switch off the standby power source. Number three, it must be able to control the genset. So switching on, switching off the genset, starting it up and shutting it down, shutting the engine down safely and under the right conditions. So let's look a bit more closely at the transfer situation of the ATS. So the ATS diagrammatically looks like that. So you have two main sources of supply. You have your mains or utility supply, which is here. So this can be KPLC. And you have your standby generator, which you have installed in your system. The loads that are connected are down here. And these you can see electrically are connected both to the mains and also to the generator. So the work of the ATS is all this system here. Sorry, it includes this as well. So all that system there is in place to do the simple job of switching between either the generator or Kenya Power or mains utility. So both the loads are connected to either of them through circuit breakers. And at any given moment, both circuit breakers cannot be on at the same time. Otherwise, you will have a clash of these two power supplies. So the automatic transfer unit or the automatic transfer system must ensure that there is no time when both the circuit breaker and in the utility and in the genset are connected to the load. So if, for example, you're running on standby power through this circuit breaker, this circuit breaker must be off, and vice versa. If you are running your load through Kenya Power, this circuit breaker must be off. Okay, so that is the work of your ATS. Now, the sequence of events when you have an ATS is such that it is able to sense when there is a condition that requires a changeover from prime to standby or from standby to prime. This is done through various sensors, which are shown here. So you have sensors that sense, for example, under voltage. So under voltage is anything from your main supply, say to 40 volts, all the way down to 0. So if it is at 0, it is also considered to be an under voltage, and that sensor might identify that. In addition to that, you can have a phase sequence sensor. This identifies if the direction, if you have three-phase power, the direction of that power must be in the correct sequence. So if it is the peaks of the three-phase power follow the direction of red, yellow, blue. In case the power supply at the utility is in the opposite, say red, blue, yellow, or any other configuration, the sensor for phase sequence would be able to trigger the automatic transfer logic. So these sensors would trigger this logic, and the logic in turn would send a signal to the circuit breakers to break, which we will go into the sequence of events shortly. Some of the other sensors that can be there are for frequency and for what you call transient faults. That is, it needs to be able to sense if something is a surge. So for example, a surge is a momentary problem with the system. It would not warrant the generator to be switched on fully, because generators take time to get up to speed. So it must be able to distinguish between a momentary problem and a more permanent problem, right? In addition to that, we have, of course, the transfer logic itself. This is the computer or the brain of the system, which sends signals and receives signals from the various sensors and switches, and even from the machine itself. So it can send a signal to start the generator, and it can also receive a signal from the generator indicating that it is running, or it is able to supply. Right. So now let's look at the sequence of events for operation. So sequence of ATS operation. Okay. Now, so let's say at the beginning of this sequence of events, you are running normally from KPLC. But at the first instant, you have what is called initiation of transfer. In this step, what happens is the system senses an under voltage or a negative phase sequence, or even a phase failure, any of the conditions that we had we had indicated below, a wrong phase sequence, a problem with frequency, and so on and so forth. This sensing of these will now trigger the ATS to identify that there is a problem with the main supply, and it will then initiate the breaking of the main breaker. So in the first step, it senses that there's a problem with the main supply, and it disconnects the circuit breaker, or it opens the circuit breaker after a suitable time delay, of course, to ensure that there are no transients. It is a permanent problem with the system. So that's initiation of transfer. The second step is dead bus. So in order to explain this step, we would then need to define what a bus is. So what is indicated there is you have, for example, this is called a load bus. So a bus takes its name from what we call bus bars. So bus bars represent lines that have the same voltage onto which different sources or loads are connected. So if you have red, yellow, and blue, for example, they can be connected to a generator. They can be connected to a second generator here, but they can also be connected to some loads. All right. This set form a bus. So a bus is a common set of lines onto which voltage can be taken off or on, and it is used to connect various sources and loads. So when we talk of a dead bus as the second step of the operation of the ATS, just get rid of this. When we talk of dead bus as the second step of the operation of the ATS, or the changeover from mains to standby, we point out that we have already seen the circuit breaker is off. So that means that there is no power coming from here, and at the moment there's also no power coming from here. So what this means is your load bus is de-energized. So it is considered to be dead. So you de-energize the load bus. This essentially, what this step is, it is a point where you give a time delay for any residual, for example, capacitive currents that are flowing, any inductive currents that are flowing, for them to die down to the point where the voltage of the load bus is zero, right? There are no currents that are flowing. This is to ensure that your system is safe and it can be switched into the next step. So the third step after dead bus is generator starting. So once we've ensured that the loads are not receiving anything, there is a dead bus there. Generator starting, sorry. Once we've ensured that our bus is dead and it has no supply from anywhere, it is then safe to start your generator. So a signal is sent from the ATS logic to the generator, the standby generator, for it to start up. Yeah. Then it starts up, and when it attains the voltage that is required, this is sensed through what we call VTs. VTs are voltage transformers. The purpose of VTs is to step down voltage so that they can be used with instruments. So instead of submitting the instruments to 415 volts, you power them through VTs, which supply a proportionally small amount. So when you have started up your generator, it is up and running, the voltage is ready, it is at the proper frequency, the system is ready now to connect to standby power, in which case you go to the fourth step, which is completion of transfer. So during the completion of transfer, standby power is now available at this point. So you now have voltage that is ready to be supplied at that point. So completion of the transfer means that you now connect, you close the circuit breaker that connects the circuit of the loads to the generators. Remember, your circuit breaker here is open, utility is no longer available, but now your standby is available from here. So you can close this, and that then now completes your circuit and you're able to supply your loads. So you're now on standby power. Okay. So this is the sequence of operation for mains to standby. What is the sequence of operation for standby to mains? In this case, you reverse the sequence of events. So your first would be generator shutdown. So you shut down your generator and you switch off your circuit breaker, right? You disconnect. Actually, it's not shut down, but rather it is generator disconnection. So technically, you don't need to shut it down. You just need to disconnect. Once you have the generator disconnected, you then follow the sequence that we had said before. You then need to have dead bus, whereby you give a delay, a time delay, to allow any circulating currents to de-energize from the loads. So at this point, we have now your circuit breakers on both sides being open. The loads are completely without any source of power. So number 3 would be reconnect mains. So that is, you ensure that the main supply is back on track, and then you can complete the transfer. So completion of transfer in this case, transfer. these are generally the same step because you do not have any startup operation for your mains utility. Yeah, in most cases, they will not be two different steps. Okay, and of course, there you have your ATS and its operation. Any standby power and any mains power can be intermittently used or interchangeably used to supply loads as required. And I think we can stop there for now.